Okay, so the first hour we talked about paying into an ordinary annuity. We had mentioned at the beginning that there's something called an annuity due. And we had mentioned that an annuity due is when you pay in at the beginning of each period. So let's say that we have our timeline for our annuity. In the end of each period, there's our periods broken down in our timeline. In an ordinary annuity, whether we're paying in or drawing out, the payments are made at the end of each period. So for this example, I happen to have 14 periods. The 14th payment into this is at the end of that 14th period. So if we're going to turn around and start drawing it right back out, that last payment doesn't really even draw any interest. It's before we start drawing out. It's just paid in, and then we turn around and start the liquidation process. On an annuity due, however, the payments are made at the very beginning of each period. So you can see that 14th period payment or last payment is made with a month left or one period left. So it gets to draw interest for one period. In fact, each of these payments draws interest for one more period. This first payment in the annuity due sits there for a month and draws interest before it would have even been made in the ordinary annuity, or a quarter or a year or whatever our period is. So because of that, there's a slight adjustment factor for an annuity due. So the future value for an annuity due is that same formula we had before, that regular payment times 1, 2, 3. 1 plus our rate divided by X, which is the number of periods per year, to our power of our number of periods minus 1, close, divided by, open parentheses, our rate divided by our number of periods per year again, close and close. So that's exactly what we had before. Now comes the adjustment factor. This is the part that is the difference. So we times 1 plus the rate divided by the number of periods in a year. That's just the interest for a single period. That's the compounding factor for a single period. So let's take a peek at this. Let's say that we are going to find the future value of an annuity due for, let's do $400 per month at 10% for 20 years. So we're going to put this into our formula. It's going to be $400 times 1, 2, 3, 1 plus 0.10 divided by 12 to the power of 20 times 12 periods a year is 240 periods, minus 1, close, divided by, open parentheses, 0.10 divided by 12 again, close and close, and now it's our adjustment factor here, times 1 plus 0.10 divided by 12, close. So let's punch this in. 400 times 1, 2, 3. 1 plus 0.10 divided by 12. Close. Power of 240. Minus 1. Close. Divided by open. 0.10 divided by 12. Close and close. Now if we hit equals here, this would just be our future value of an ordinary annuity. Times, open, 1 plus 0.1 divided by 12, close. So 306,287.76. Is it 278? $278.76. Thank you. Had this been an ordinary annuity, what would the balance have been? Well, I just divide by that adjustment factor again. $303,747.53. So it makes a difference of about $2,500, a little over $2,500, to have an annuity due versus an ordinary annuity, because you get 1 month's extra interest in this case, or 1 period's extra worth of interest. Find the future value of an annuity due for $1,200 per quarter at 9% for 30 years. So find that for me. So we're going to get a future value. It's going to be $1,200 times 1, 2, 3. 1 plus 9% will be 0.09 divided by, it's quarterly, so divided by 4 to the power of 30 years times 4 periods a year is 120 periods. Minus 1, close our parentheses, divided by 0.09 divided by 4, close and close, times 1 plus 0.09 divided by 4. 1,200 times 1, 2, 3. 1 plus 0.09 divided by 4, close parentheses, power of 120, arrow out, minus 1, close, divided by open, 0.09 divided by 4, close parentheses, times, parentheses, oops, I gotta have 2 close parentheses there, I gotta get that done. Second one there, okay, now times, open, 1 plus 0.09 divided by 4, close. So that gives us 732,893.86. $86, not 36. So 732,983. Wow, I've been horrible on my numbers today. 983.86. I think I finally got it right. How many of you had that for balance? Okay. Sorry about the confusion there. What would it have been if it had just been an ordinary annuity? Well, let's divide it back. Divide out that conversion factor, that adjustment factor. 1 plus 0.09 divided by 4. Would have been only 716,854.63. So you can see in this case, It's over 16,000 difference, 16,127 about difference to have an annuity due. So here's what I want to find. Find the difference in interest between an ordinary annuity and annuity due. For $4,500 per year at 12%, actually let's go 11% for 30 years. So I want you to try that, see if you can come up with what that difference is. So let's find ordinary annuity. So that future value would be 4,500 times 1 plus 0.11. This is per year, so we divide by 1 or just leave it. The power of 30, because it's only 1 period a year for 30 years, minus 1, close, divided by 0.11 divided by 1 again, so just 0.11, close and close. So that's going to be our ordinary annuity. Let's see what that comes out to be. $895,593.95. How many of you came up with that? Perfect. $895,593.95. So now for an annuity due, all I have to do is multiply by that adjustment factor. So I'm going to just multiply that balance times 1 plus 0.11 divided by 1. So I don't need to do the divided by 1. Which would be 994, 109.29. That's the annuity due. So I'm going to have to take that 994, 109.29 and subtract. What's going on? $895, 593.95. So $98,515.34. I take that as a good sign. Okay, any questions on that? So that's our annuity due. Now the next phase is to switch over to, if I want a certain amount, how much do I have to pay in each month or each quarter or whatever? So the required payment is equal to that desired future value divided by, and of course this is still ordinary again. The rest of this formula is going to be exactly the same. 1 plus r divided by x to the power of n minus 1 close divided by r divided by x close and close. So the only difference is instead of putting in the payment here, we put in the future value, and instead of multiplying, we divide. only difference. So let's see what we come up with for an example here. Let's say that you feel you need $400,000 in 25 years to retire. I know how much you need to put away per month at 9.5%. So we're going to put in here, our payment is going to equal $400,000 divided by 1, 2, 3. 1 plus 0.095 divided by 12, because it is monthly. 25 years times 12 is 300 payments, or periods, minus 1, close parentheses, divided by 0.095 divided by 12. Close and close. So 400,000 divided by 1, 2, 3. 1 plus 0.095 divided by 12. To the power of 300, out of there, minus 1, close, divided by, open, 0.095 divided by 12, close, and close. What's wrong? We'll just re-enter it, probably quicker. So let's try this again. 400,000 divided by 1, 2, 3. 1 plus 0.095 divided by 12. Power of 300 minus 1 0.095 divided by 12. Close and close. My fingers crossed. What'd I do? Do I? Okay. Let's try that again. It's not going to be my night, I don't think. So 1 plus 0.095 divided by 12. So power of 300 minus 1. Close. Divided by 0.095 divided by 12. Close. Close. Hey, we got an answer. 328.12. So to have $400,000 in 25 years at that interest rate, we have to put away $328 per month. What do you think? Other than my calculator typing skills are pretty poor tonight. Let's do one more example, see if I can get this one right the first time, and then we'll go from there. Find the required payment for $250,000 in 40 years The required, we're going to go monthly payment again. 40 years at 13%. So that payment's going to be the $250,000 divided by 1, 2, 3. 1 plus 0.13 divided by 12. Close. Now 40 years monthly, 40 times 12 is 480 periods, minus 1, close, divided by open. 0.13 divided by 12, close and close. $250,000 divided by 1, 2, 3. 1 plus 0.13 divided by 12. The power of 480 minus 1, close, divided by open. 0.13 divided by 12. Close and close. We get $15.45. Now I realize 13% is a pretty good interest rate, but 11 or 12% is not impossible. If you have 40 years, so those of you in your 20s looking at 40 years to retirement, 15 or 20, 15, 20, 30 bucks a month isn't that much, and that is a significant contribution into your retirement. In fact, here's what I have to do just because it's me, and I like to point out stuff that can be painful. I don't know how many smokers we have in here, and I'm not criticizing anybody who does smoke, because I used to smoke myself. It's been quite a while now, but now that you're looking at $7.50 or so a pack, let's say you're looking at 6 packs a week times $7.50, you are looking at $45 a week. Times 4 weeks a month, that's $180 per month. And let's say that you are 18 years old. And of course, you're looking at retiring probably 67 or 68 years old. So you're looking at 50 years worth of smoking between now and retirement. And let's go at a relatively conservative 10%. If you had taken that money that you used to buy cigarettes, and again, I'm not trying to criticize cigarettes, I'm just pointing out the economic side of it here. 180 times, now we're using the payment to find the balance now, the future value. 1 plus 0.10 divided by 12 to the power of 50 years times 12 months in the year is 600 months, minus 1, close, divided by, open, 0.10 divided by 12, close and close. This will make you cry. 180 times 1, 2, 3, 1 plus 0.1 divided by 12, close, power of 600 minus 1, close, divided by, open, 0.1 divided by 12, close and close. Any guesses? Or some of you already figured it out, I'm guessing. Yeah, that's painful. At 10% interest, starting smoking at 17 or 18 costs you, if you're a 6-pack a week smoker, which most people are lighter than that. Even at 3 packs a week would cut that in half. But you are still looking at $1 million habit. That's your depressing thought for the week. Is there a table for this? Well, the table for this is the same table that we use for future value. Just instead of multiplying by the factor, we would divide by the factor. And of course, once again, there aren't too many percents and periods that fall into this. So let's say find the quarterly payment required to have, let's go 750,000, $750,000 in 20 years at 8%. So I need two things. I need I need my rate per period. What's my rate per period going to be? %8 is my annual rate, divided by, this is quarterly, so divided by 4 is going to be 2%, will be my rate per period. I also need to know my number of periods. That'll be 20 years times, since it's quarterly, 4 periods per year is 80 periods. So in the table, 2% and 80 periods gives me 193.772. So instead of multiplying, I'm going to take my 750,000 divided by 193.772. That's 3870.53. So to do that in 20 years at 8%, you'd have to put away just under $4,000 per quarter. Now the reason I went 20 years is, of course, this table only goes up to 100 periods. So I could have only gone 25 years would have been the max I could have gone up to. What if you need to go past that? Well, that's where the formula has to come in. On the compound interest table, you could just do it, break it into half of the period and go from there. But since there are regular payments being made in, you cannot do that with an annuity. Let's have you guys try some here. This one, you're going to use the table. Find the required payment let's do annual payment to achieve $350,000 in 40 years at 9%. So use the table to find that. We'll discuss that in just a second. So we find our factor in the table. This is going to be, because it is annual payments, 40 periods, 9%. What do we get out of the table? $337.882. Is that the factor you guys found? So we are going to take 350,000 divided by that. Gives us 1,035.86. So over 40 years, you'd only have to put away a little over $1,000 a year to have 350,000. Let's have you try one with the formula now instead of the table. Find the required monthly payment for $800,000 in 45 years at 13%. So our formula is going to be 800,000 divided by 1 plus 0.13 divided by 12 to the power of 45 times 12 is 540 minus 1 close divided by 0.13 divided by 12 close and close. So let's see what we get. 800,000 divided by, open, 1 plus 0.13 divided by 12, close, to the power of 540, arrow out, minus 1, close, divided by, open, 0.13 divided by 12, close and close. Now before I hit enter, what did some of you guys get for payments? $25.83. There it is, $25.83. That's the power of being young again. Okay, it is 7:10. It's a few minutes early again, but let's go ahead and take our second break here. We'll start lecturing again at 7:20, and we'll finish up with some examples and some comparisons between compound interest and annuities.